China. Everything, including circuits and everything, is made in India. And when we gave keyboards, they said, hey, we don't have computers. So Navneet remembers, we used to buy this $9 Linux computer, and we used to stick it behind the monitor and then connect our keyboards. So that was the computers that we installed in a lot of rural schools. And then they said, sir, you gave us keyboard, you gave us computer, but we don't have any concept of labs. The labs didn't exist for them, right? Because they need to know English to type their mother tongue. So they're first learning English, so they have been completely kept away from computing or typing. So for the first time now they can type in English as well as their mother tongue, and that's what we did. We patented this keyboard here in Orlando, then we started making the hardware, and I used to go to India back and forth. And finally my wife said, once we got the patent, she said, go back to India, finish it and come. So I told her I'll come back in 6 months. It's been 7 years now. So that's what I'm telling. So this hobby, the beauty about it is, I built a robot in India, 1983. I'm going to take a little bit, 5 minutes.
Oh, no, please take how much ever.
So 5 minutes I'll take, and then you guys tell me about your project, so I can share this with other kids. No, I'm fine. So what we did was, just like for the annual day in my school, engineering school, they said, hey, nobody wants to come see the mechanical engineering lathes and all this greasy stuff. Can you do something? So what I did was, me and 2 of them, we built just like with a paper cardboard box. We built like a robot thing, and we put some LEDs on a Wix, like a web drop, you know. We made holes and I put my radio. I was a radio amateur. I used to build transmitters. I used to talk to people around the world. So we put our radio things and the mic as a nose, and then we put a coat and tie, and then in the corner there was a small hole, and my friend used to see from the hole and speak. So people were stunned. They said, how can this robot know about our color, and they're looking everywhere, they cannot figure out how this. Next day, a lot of people from around the villages came by. They said, hey, there's some thing telling, fortune telling machine has come. So they used to say, I lost my cow, can you tell me? So they used to say, hold me your eyes, hand in front of my eyes. And they could not control the crowd. They had to bring the shutter down and disperse the crowd. So we felt bad. We felt that we cheated, right? So we wanted to build a real robot. We had no clue what a real robot is, right? This is 1983 we're talking. So we got 5 books from MIT. Michael Brady was one of the books that I followed. You guys might know him. He's one of the top guys who wrote those books in a long time. So we did everything. We built, there was the only computer in the university we had. We simulated and showed it to our professors. And we borrowed 40,000 rupees from my professor, 40,000 from Indian Institute of Science. That's one of the premier top institutes in India, #1 rank. So 80,000 we borrowed, imagine. People said, that time it was a big amount. People said, you're not going to graduate, but we never gave up. But there were a lot of failures every day. So my dad's moped was parked in railway station in Bangalore. So it was 3 hours to go to Bangalore, right? We can't find a nut and bolt. We used to go. And every night I come back, 6 o'clock I reach, 6 to 8 we reach, go into my principal's room. He had given us his entire room. And something fails by midnight. Again run, 6 o'clock train, reach Bangalore by 9, do something, reach in the evening. So this went on for 6 months. Everybody graduated and left. I'm the only guy. So imagine. So we got our grades and degrees. I got a job in Indian space, like the NASA equivalent. I postponed it 3 times, and then finally the chairman said, we'll let you go play with your robot every weekend, please come and join. So they had hired about 6 robots with people who have done robotics projects. So that's how I got into robotics. And that's how I got into, I came here to do space robotics on the space shuttle. Because in India they told me next 20 years we're not going to build robots in space. So only if you do your PhD we'll take your resignation. For masters we're going to send you to Indian Institute or IITs, don't worry. So that's how I came to Orlando, because to work on the space shuttle robot. So when I came here, then I realized that that arm is called Canadian arm, owned by Canadians, not US. They don't let anybody work here. It was crazy, right? So then I started doing my masters. I still worked on my masters on flexible arms for the robot, making flexible arms. And then I used that to do a lot of other things. I used that to build the first autonomous helicopter that the actual code was run real time on a pilot with the pilot control disconnected midair.
Wow.
Midair. Now I sweaty, wake up sweaty. They never told me they were going to do that. So whatever I did learned in this robotics was used there to build that, running the code in parallel to calculate the torque and forces like a robotic joint, right? So you have to go from bottom to tip, and then from tip to bottom to calculate the torque values, right? Or things like that. But they made me run everything in parallel. This is many units, so you can run it in real time. So that's what I did, and that led me to a lot of other things, right? I did the first space docking thing. If you go look at it, I'll send a link to you guys. I'll send to Shamla. So robotic docking. So even as on date, we don't have a refueling thing yet. So how do you do that at 17,000 miles an hour? How do you make them dock? How do you make the, even if a millimeter off, you're off, velocity is off, tremendous force, right? Everything is destroyed. So how do you do all that? So that's how I got into a lot of these things. So that's why once a robotist, always a robotist. So you all are robotists now, right? For the rest of your life. But I keep watching. I see Suresh posting on LinkedIn, so I'm glad I could come and see you all. And I'll let you explain to me little by little about your different components of the project, because all this, what we've done is we've put these labs in various schools. They don't have the resources to build robots, right? So at least they can learn. By looking at what you're doing, they can learn and be motivated. And that's why I'm here, okay? All right, I'll let you guys.
So, my name is Anup, and just a little explanation about our game.
Okay.
So we play on a 12 foot by 12 foot. We play on a 12 foot by 12 foot.
Let's start with like what first is and everything, so we know. Sai, why don't you start with that?
No, I can do it.
Okay.
So we're FIRST Robotics team. We're FIRST Tech Challenge team, a part of an organization called FIRST. And FIRST is a global nonprofit with teams across worldwide. And FIRST stands for Inspiration and Recognition of Science and Technology. So there's different levels to FIRST. There's FLL, FTC, and FRC. So we're an FTC team, FIRST Tech Challenge. And every year there's a new game challenge that we have to design and build a robot to solve. And so they can kind of talk about what that is.
Yeah, so this year on our playing field, we were given several of these hexagons called pixels. And the main objective of the challenge this year is to control these pixels and score them on the backdrop. This is over there. So they're placed on either stacks here or in the corners by a human player, and a robot has to come pick them up, drive from one corner of the field to the other corner of the field, and score them. And so I guess Arnav can explain how we accomplished that this season.
Yeah, and so hi, my name is Arnav. I'm another build lead on the team. And the way we pick up the pixels is with this intake system right here. We designed this like double jointed roller, double stage system. So we have one servo on a linkage here that can lift up this ramp. And like while we're driving around, it's up so that it doesn't drag against the field. But then when we're picking up these pixels, we drop it down so it's against the field and it can move smoothly up, smoothly up the ramp. And then we have these rollers on a passive. Yeah. So and then we have these rollers on a passive linkage, and the passive linkage gives it like another degree of like flexibility, so that when we actually intake the pixels, there's a little bounce in it, and it gives it like the right amount of force to keep on intaking the pixels. Like intake.
It's stuck on the ground. Yeah. It's on the mat. I think it's a folder. Just
Yeah. And so once we intake it using these rollers, it sends it. It sends it to our depositing mechanism, and what we have is just this bay that can hold the pixels in there. It can hold 2 at a time, which is the max amount we're allowed to hold. Lift the back one. Yeah. So it holds 2 just like this, and then holds it in place with these little claws that just drop down and up. And then we have these sets of linear slides here. We just strung them in order to lift it up so we can score higher there. And then like once we get to the exact height that we need, we can plug out the depositing mechanism.
Yeah.
just like that. And with this, we can get like so that the bay is at the right angle, the same angle as the the backdrop, and that way we're able to like score more like effectively and accurately. Yeah.
Can we like move all the way? Yeah. It's like our robot can't go.
And a special part about our drivetrain, you can see this is normally like in a car, you have to turn the front wheels and then you can turn the rest of the car. But we actually use special wheels called mecanum wheels. I can show you here. And so each of these wheels has like rollers at it, mounted at a 45-degree angle. And what this does is if you run each wheel at a certain power and certain speed, you can move side to side, like we can show you. The friction of it pushes it side to side. You can move diagonal, and obviously straight. So you can move in all sorts of directions. It's
Very nice straight.
okay, yeah. And so we designed these all in SolidWorks CAD, and then we send it off to a company to get it metal cut. These are just aluminum plates, and then we design everything else around that. All these orange parts, I actually have a 3D printer, so I can 3D print all of these once we create the files for it. And yeah. Actually, another part about the game challenge that Anup didn't mention is the drone launcher. So we actually have to shoot a paper airplane. We have to shoot a paper airplane accurately. You can see there's these zones here. So if we get it in the closest zone, it's like 30 points. If we get it further, it's like 10 points after each zone.
Okay.
You can show us like 3
Yeah. And so we just have this spring-loaded mechanism. Yeah. We have this spring-loaded mechanism on like a linkage system, so that once we pull this spring back, it locks it in place, and then when we're ready to shoot, it just flings it out and shoots the paper airplane a certain distance.
Nice. Now, one more time. How were you able to slide?
With the mecanum wheels? Yeah. You can lift it up all the way driving. I'll drive slow, and you can see how, yeah.
So basically, each
It's
roller is at a 45-degree angle,
Uh-huh.
and they're kind of like aiming towards each other. So when you're going left or right, one set of wheels go to like spin like this, and the other go like this. So like pushing movement.
Oh, I see.
Yeah.
If you spin them a certain way, you can get all sorts of movement.
Yeah.
So this place where I set up my factory in Bangalore, that's in a university called NITE. And their team, now the Indian Space Research has given they're going to pick, it's a robotic competition to go, they're given a challenge to go on the moon surface. They're creating an artificial surface.
Yeah.
Your grandpa's house, right? Chalkere.
Yeah.
So that's where they're going to be testing it.
Okay.
Because that place is so similar to the moon surface. And the space shuttle equivalent just landed there last week. Their flight tested there. So his hometown is going to be a big, famous place now. It used to be a desert, right?
Yeah.
Nobody could, but now it's going to be pretty good. Now, so they have been selected. So they are also doing a rover design and so on. That's why I'm trying to connect you guys. This is a little college level team. They were, but the mechanism is not so complex. You guys have done a great job on this.
Talk about the older parts.
Yeah, and so the game is separated. It's like a 2-minute and 30-second game. The first 30 seconds of the game is fully autonomous, so it's pre-programmed. We code like using Java.
And it uses like webcams to detect different things, and depending on what it detects, it'll perform different things.
Yeah, so we use different sensors during the autonomous period. We have a touch sensor here to see if we're against the walls. We have the camera. Those little QR codes, they're called April tags.
Okay.
That's all.
And so what we're able to do is align with them to make everything more accurate.
Okay.
And then, yeah, we have limit switches to tell when things are clicked. These different sensors. But this is something called odometry, which just like in a car, you have something that tracks the mileage. This tracks how far the robot's moved across the field.
Okay.
It's just these 3 wheels, 2 going forward, so you can tell if it's turning the heading of the robot, which way it's faced, and then 1 going sideways, so you can tell how far it's moved in this direction.
Show the encoders that it is attached.
Yeah, and so it just uses these encoders. It's like a dead wheel odometer, so the wheel isn't actually active.
Okay.
It just spins this encoder, so that like if we move forward, the wheel spin like a certain distance, and we can calculate that in code, and it just makes each movement more accurate.
Okay. So you have to, they have some restrictions like that. Some part you move the joystick, and then it has to go autonomous.
Oh.
So what I was trying to tell them was, in space, particularly in robotics, particularly space, we have something called triple redundancies. That means if one fails, what's the second option? That fails. So without that, people don't let you fly anything into space. So it becomes very hard, right? Extra items and stuff. So we have to be very careful how you add weight. So one is as though you didn't have any camera working.
Yeah.
Right? Something got covered or some dirt is there. So how do you go with just encoders? That's the first assignment I told them to do. Imagine that you have been given coordinates and you've got what we call as dead reckoning. Do you guys know what is dead reckoning?
Yeah.
Okay, yeah. Between those 2 points, you got to find your coordinates, right?
Yeah.
So that was my first project here in IST in UCF, Simulation Institute, was dead reckoning 2 F-16s dogfighting. Because when you build a simulator, right, so I can't get these accurate positions to do a fighting, right? So you have to have a fair fight, right? So if this position is coming in a delayed manner, then you have an advantage, you're going to shoot it now, right? So we have all this problem with fair fight. How do you know this training is effective? How do you train it? So we have something called dead reckoning between those. First order, second order, third order, until the new signal comes. So that was my first project doing for the simulators, doing dead reckoning, right? That's how we have now simulator networking standards that you guys see. So that's all was done here in UCF. Yeah, go ahead.
Oh yeah. So like we just add as many sensors as we can to make
Okay.
everything as accurate as possible.
How many do you have in total?
20.
20?
20 sensors.
20
Yeah.
sensors. Wow. Okay.
So each of our drive motors, we have 4 drive motors. They have encoders inbuilt in the motors that
Okay.
allow us to see track its amount of rotation.
What kind of motor is that?
Oh,
It's like there's a company called Gobilda. They sell all the parts for FTC.
Okay.
Or not all of them, but they're one of the companies that sells parts for it.
Okay.
So these are all the motors you see are off the shelf. All the servos,
Okay.
they're off the shelf.
It comes
Yeah.
with the encoders, you gotta buy them.
Yeah,
separate.
Yeah, they come with the encoder is built into the motor.
Built in.
Yeah.
Okay.
Yeah.
So you basically, there's different vendors for different robot materials that you want to do. What we use is Gobilda,
Oh.
but they use mostly the electronics part of it, but everything metal and all, they custom design it.
Yeah, like we buy from these off-the-shelf companies, like all these channels, this channel here.
Uh-huh.
But like ideally, we want it as custom as possible because when we design all these parts, we make sure that everything fits together perfectly.
Okay.
We can optimize each and every single component. Like previously, we used to have this, just having a channel across, but
Okay.
we switched to this this different sort of brace that I actually custom designed.
Tell him what the brace is used for.
Yeah, so in the middle of the field, we actually took it apart because like it was just in the way. But
It's like a one-way swing, and our
Yeah.
robot is like an inch too tall,
Uh-huh.
so it'll open this way, but to go back this way, it doesn't clear.
yeah,
So this wedge like pushes it up.
yeah this
Yeah.
gate during the match, you can all robots can like easily go through this way,
Okay.
but
So,
it's constrained by these rods right here,
Okay.
so I can't go back the other way.
Okay.
Yeah.
And just to make it easier on the drivers, so they don't have to only go through these paths.
Uh-huh.
We designed this angled piece that is just at the right angle that it pushes up the bar.
Yeah.
That is going this way, right?
It's going this way,
when we
Yeah.
drive the other.
but when we drive this way, it's like normally we won't be able to
Like
go.
this doesn't go.
Yeah.
So this pops it up a bit.
Okay.
It pushes it up. Yeah.
Suspension.
Yeah,
Yeah.
and then the third part about the game is we actually have to hang our robot.
Okay.
So if you see here, we have these 2 hooks,
Oh. Okay.
and so we have to hang off of these poles.
Okay.
Yeah, sure.
Oh, I can't drive. Just align it.
It's very important for them to find the correct optimal balance between like what the weight of the robot is and so they still don't compromise the functionality,
Oh, I see.
but at the same time are able to like, put
Yeah.
the robot on.
That was one of the big design constraints.
Uh-huh.
Oh, he wants to.
Yeah.
Do it the other way, so it's good for taking the picture.
Oh yeah. Catch it. All right. I'm gonna.
Yeah, those are some of the big design constraints this year.
Okay.
We have to make the robot as light as possible
Okay.
so that we can hang the robot. Like you can see, all this pocketing that we did
Yeah.
here, the head pocketing on the drivetrain, we have pocketing too. So we made sure that each part was as light as possible. And then also, with these bars here, and the door in the middle,
Uh-huh.
with these bars, we had to keep a minimum height for the robot. So our robot's around like 13 inches.
Okay.
And so we had to fit all of the robot into this very compact package and also light.
Okay. Very nice.
Can you tell a little bit of lessons learned through the season?
Uh,
Somebody else talk?
yeah.
Yeah.
So one of the during the earlier stage of the season, we had a problem with our odometry not functioning properly. So between last season and this season, we switched from a 2-wheel odometry system to a 3-wheel odometry system. So the difference between both is a 2-wheel system relies on the IMU to determine the heading of the robot.
Okay.
But a 3-wheel system, like Arnav said, uses a third encoder wheel to determine that heading. It's just so much faster than an IMU. So we had a problem implementing that into our robot because we had strafing issues.
Mhm.
So when we wanted to go forward, for example, it would veer off if there was drift.
Oh.
So while trying to fix that, we learned that our drivetrain was bent.
Oh.
So the plates itself were not aligned, and it was pushing the wheels.
Oh.
So we rebuilt our drivetrain, and this solved our problem. So
Oh,
that was one of the challenges we had.
Oh.
What really caught my attention is when Uncle was saying, the different points and how you tried to find the trajectory between those two. They use
Yeah.
something called quintic.
Yeah. So to generate, during autonomous, we have to we use our odometry pods
Mhm.
to generate
The next-
paths for the robot to follow.
Oh.
So one of the types of paths we can generate is a non-linear path.
Okay.
And so to do this, we use quintic trajectory,
Okay.
which allows us to generate a non-linear curve using a 6-variable equation.
Mhm.
And it does something very similar to what you said.
Right.
We create a bunch of points along the curve so we can follow those points
Mhm.
and get an accurate and smooth movement
Smooth movements.
across those points.
Right, right. Yeah, we used to have this first order, it goes, jet goes, corrects, jet goes, corrects.
We
right?
have something very
Yeah,
similar to
yeah.
that too. We have a PIDVA correction system
Okay.
during movement, so we can take in the position. We know what position the robot is using the localization system provided by the odometry,
Okay.
and we know what position the robot needs to be using the quintic trajectory generation.
It's called twin tech, is it?
Yeah, because there's 6 different equations. So we use a quintic spline. There are other versions that do the same thing.
Okay.
But that's the one we
That's
use
the one.
because it offers more accuracy in terms of variables we can control. So we know, because we know those 2 points, at every single point we're able to correct and go back to the original.
Ocean.
Yeah,
Okay.
so we do something very similar as well.
Very nice. There's something called look ahead we use. Look ahead. You guys know what a look ahead is?
No.
Oh, is that a view forward?
Like you guess, now using your dead reckoning you kind of know, right?
Yeah.
So you're here. By the way, I was the first person to, my PhD thesis was on dynamic terrain, how to model terrain, like a real terrain. Because when a tank drives, it destroys the ground. So the next driver doesn't get the same feel, right? It costs about $500 to drive a mine. So they wanted us to build a simulator to do as many times you can do on a simulator, right? So that's what I did, building all this knowledge of mechanical systems into connecting with the terrain properties. So we got all these values from World War II. In World War II, what they used to do is they used to drop these cones from helicopters. So depending on the kind of slush in the ground or how soft the soil is, different colored plumes come out of that. The deeper it is, the different color comes. So the tank driver knows, hey, there's 2 yellows, I gotta go between 2 yellows. Because if one guy gets stuck, the rest of them are stuck, right? So they used to use, that's called a cone index. So it's a composite measure of shear stress. You learn later on in engineering, shear and tensile stress, combined measure. So we use those data for the terrain properties. So, and then we had the graphics. So we're really driving as a zip tank, right? With actual models of transmission, slip, and everything getting calculated in real time, including the visuals. Now, there were, somebody saw this and gave us these coordinates from Mars, right? So it was an oblique angle, like, just like your payload issues of, different sensors can only have so much place. So it was at an angle. So it used to obliquely detect the point height value and give it back. It's called point cloud, right? So then we use the point cloud and we built a surface around it. We call it triangulations. So, and then I was able to drive on Mars, right? So it was crazy, right? At that time it was not. It was just like you guys, overnight we spent times at Simulation Institute, and then I drove miles and miles and miles. There's nothing on Mars, right? That's when my interest in deep space went off. So sometimes, the process of learning, right, takes you. You know what? Even JPL folks came from NASA, they came to Orlando. They said, hey, at that time the rovers had not gone in the Mars yet. They said, we want this for our design center. We want to simulate this. But the US Army wouldn't let us. They were busy with their own programs. They said, we are not interested. But that's how I kind of drove on Mars. Okay. So great. So you were saying something about the look ahead, right? Look ahead is what we do is when I was going on Mars, we found a lot of cracks. I mean, none of the rovers have detected it yet, but there were a lot of cracks. And I tried triangulating, trying to find maybe some mistakes, but could be there's a lot of earthquakes happening there, or the impact that happened that took 1/3 of Mars away. That's how they lost water, right? So that could have caused a lot of cracks. But if the surface is covered, you don't see it in any of the pictures. Fine dust is covering it. So now when I drive the tank, I need to look ahead to figure out where I'm going to be in the next few seconds, right? So based on that, I'm going to use to calculate the orientation like what you did. I may use this and this positional information.
Correct.
Right? Correct. Or I may use, once I cross this small forge or something, once I cross, then I use that and this, calculate the orientation, right? Otherwise, when I'm like this, my camera is like that, right? So I cannot get the ground coordinates. So we used to do a lot of that. So I need to do look ahead. If I'm going at this velocity, this trajectory, where am I going to be in the next few seconds, right? And there could be slip and other things. You may not be exactly where you want it to be. And same way that you're calculating your positional information. So we used to calculate and find the errors, differences. So that's what we call as look ahead. So you can kind of predict in advance certain speed and other things, right? Yeah, go ahead. So, who's next? Yeah.
So why don't you guys just explain each one of you what you do in the team as a part of the team? Like someone is doing outreach, and someone will be doing marketing or finance. So just explain all that. Yeah.
So my name is Anu. I'm the co-captain, and I'm also the robot lead, so I work on mechanical and programming on the robot.
Yeah, my name is Arnav. I work on the robot, like all the 3D printed parts and all parts.
My name is Arhan. I'm a rookie programmer.
You're a what programmer?
Rookie.
Rookie programmer. Okay.
My name is Akita. I work on the business and the network.
Okay.
My name is Melville. I'm the co-captain of the outreach lead, so I manage like our team kids back to training the system.
My name is Anisha. I'm on the team.
You're the
Rookie builder.
rookie builder. Okay.
I'm the lead. I work on Robo with Luke and Arno, and also do outreach.
My name is Krish, and I'm a rookie programmer.
My name is Shrishti and I'm rookie in business.
Okay.
My name is Anisha and I'm shadowing.
You are
Shadowing.
shadowing.
She wants to join next year.
Next year. All right. Okay.
My name is Prithvi and I'm a rookie builder.
Okay.
Hi, my name is Praneesh, I'm a rookie builder as well.
Hi, my name is Shreya, and I'm one of the software leads on the team.
Oh, good. So, what kind of software you guys use for this right now?
So right now we have OpenCV. We have a variation of OpenCV that's designed for this gameplay. It's called FTC Vision Portal. So those two are being used for either object detection, or we have these QR codes right here.
Okay.
We detect those and we take in distance as well as heading from there to
Okay.
localize according to those images. As well as we also use odometry on our robot. I think you probably heard about that, yeah.
And then we program in Java, and we use Wi-Fi Direct to communicate our code to the controller.
What do you do Java for?
So these are all Android-based devices, so we just use Android Studio.
Yeah, so like
Java.
the actual controller in the robot, they're called RevHub. They basically have like a tiny Android chip inside of them, and then we have another like Android device here.
Oh,
It's just like an
Plug
Android
in our
terminal.
devices, run our program.
And so it just connects via Wi-Fi.
it's called. Well, did you say RepRap?
RevHub.
Rev.
REV Hub.
Rev Robotics is another electronics company we
Okay.
use.
Oh, I see.
Yeah.
Yeah. We use RepRap.
Mm.
RepRap is a board that we use.
Oh, yeah, I've
controller
heard of it,
board,
yeah,
right?
yeah.
The same thing that you use for 3D printer.
Yeah.
It's got about 6 ports for servos.
Yeah.
So we use that. We have a typing robot. Test the keyboards.
Oh.
So we use that because every button has to be tested, right?
Yeah.
I
So.
think this has 6 servo ports and like 4 motor ports.
Oh.
Yeah,
And then they have like another 6 encoder ports.
Okay.
For with sensors, different type of sensors.
So
like
Viva
digital
was a
and
part of your team, right? Group.
Pardon?
Viva was a part of your team. Robotic Home.
Oh yeah.
Yeah.
His sister's son.
Yeah.
He and 2 other kids, they did this. They 3D printed the fingers and they connected servos. And the same frame that you use for 3D printer was used for the arms to go and type.
Or like the button.
Yeah. So the fingers, it looks like that. So yeah, I mean, from a remote place like Chalkere, right? That's a very arid place. His sister's husband used to drive almost 15 kilometers, right? Through
Walk.
all the
Walk.
through all the sand, and I mean that is a replica of moon surface, they say. There's a single room classroom, right? We gave a keyboard there, and these are the kids who want to learn from you guys, right? They don't have all this resource. They want to learn. They are dying for knowledge, right? They're only let me say, sir, please tell us something about the helicopter. Please tell us something. So they're dying for knowledge. They don't have all the access. So we're giving the first step in giving them the computing device, and then they can start thinking, right? So we did for the first time we did a moon landing competition. So we selected teams from the 6 schools where we run these labs. It's called E-Bhasha labs, right? Language labs. And what we do is those teams had to come up with a creative story in Ka-Naada. That's a language in Karnataka. So the mother tongue part of the brain is here. All your creative thinking is happening here. You guys are born and brought up here, so your English is here, right? For all those people, their mother tongue, Kannada, Telugu, Hindi is sitting there. So the ideas come there. When they want to express, they go to an English keyboard, they have to jump here, right? For Ka, they have to look for K. So the creativity is lost. So that's why they're not able to do much, right? So we are giving this kind of keyboard so the ideas come up. So same like just like your team, we had given them 10 seconds restriction to land on the moon with a story. 2 seconds for takeoff, 2 seconds for separation from the rocket, 2 seconds to enter the moon orbit, 4 seconds to land. So whatever is the creative story, they start writing, they do the drawings, they scan it, just like the Scratch program, they started programming in it. And then what happened was when landing, we created the actual surface where the moon, the south surface, Indian space landed successfully, right? So we gave them the actual surface I got from the Indian Space Research, and we curated the sand. We took a picture of it on a flex sheet, put the sand underneath to look like that, and we made a small satellite with a sensor to give height values, just like the sensors you have. And they had to go measure where they want to land using the 9th map. They had to calculate the plane and all the surface normals, and then they have to put it in the simulation. Then they have to show this 10-second simulation. Very quick, right? 10-second goes just like that. But it gave them a great opportunity to combine the story, creative writing, into math skills, into the real sensor value integration. Right? That's the best they can do. No hardware, okay, but they want to learn about all this. That's why I'm here trying to see if you guys can mentor them down the road. If somebody gets donates one motor and one arm, at least they can do something, right? They can start thinking about programming. So that's what we're trying.
So we were actually talking about that for you, and then there was another non-profit, Ekal Vidyalaya, also has a lot of schools. So how we can help them, and then they've come up with a way. Do you guys want to share?
Yeah, so what we were thinking is what we can do is we can first talk to them about what FIRST is, what program we are, and what the different types of engineering, and all the basic knowledge, and then we can get them either we can get it or they can get it. However, a strafer kit, so like a pretty basic, so they can understand and see how this stuff works, and then from there, if they want to continue learning about the basics, they can do that, or we can help mentor them, turn them into like a team like we are.
Oh, that's fantastic. Ekal is a little far away from this because it's only one teacher.
Right.
So what we're telling them is at least get a keyboard and a computer so they can start doing this learning.
Right.
Then that is very hard for them. The schools we go, it's pretty much rural, right? They don't have resources. And what I've done is, we have sponsored all the classes on teachable.com. It's hosted in US. We made lesson by lesson and put it in there. So that's what I was asking Navneet and others, that you guys now can make the small modules whenever you get free. Now you got this comprehensive, but make this one by one, video record it, put it there as a lesson. Give them a small exercise. Okay, encoder, calculate this. Even though they don't have an encoder, they'll start doing this. Then when you guys give a kit, what I can do is take it as a loan 1 day a week, right? Each school gets that kit and the team selected starts working on it. Then the lab assistant, you have a lab assistant, because teachers don't have time. So we pay a lab assistant to go to school to run the labs. You see the plight, right? And there's no electricity, no internet, so a lot of challenges. Now we can take those, whatever you guys do, put it as lessons, and then hold a competition where you guys, when you come down there, you can kind of run that competition for them, right, based on your experience. And mentoring, we can also give it through this. We can their questions can be sent to you guys, and then you can answer them. That way, we can kind of take, your project to a lot of schools. So our goal is to reach at least 500 schools right now with this keyboard and language labs. Each school we put one Linux pocket computer right now, and there's a monitor. And 4 students sit, we give an earphone splitter in front of one machine, 4 kids sit. So we put about 5 machines, one is made at the server, and 4 or 5 clients. And 25 kids can do at a time. So this is the challenge that everybody, this moon landing, everybody wanted to be. For the first time, Kannada medium kids won. There's a big galata.
Oh wow.
How come our private school, English medium school didn't win?
How old are the kids?
These are high school up to 10.
Okay.
7 to 10.
7 to, so the perfect age like these guys.
Right.
Okay.
But they are very beautiful kids, so this moon landing created such a confidence among these children, right? But they don't have all this, right? So you guys can mentor them, and what we can do is, since we have an infrastructure to set up this lab and go to them, right? It makes it easy for you guys. Otherwise, you put in a place like childcare, like where Navneet is, right? There's nobody to help. There's one teacher, and there's like 4 different classes in one room. He says, okay, 5th standard, are you guys doing this? By the time you guys do this exercise for this, very difficult. That is a problem. We're telling at least set up a lab, so we can put these lessons there.
Right.
So while you're handling 7th standard, if there are 2 5th standard kids in that, they can look into that and do their exercises. Right? That's what we're telling Ekal. I gave a talk last year in the fundraising year. I came to Orlando, gave a talk.
Right.
But even today I called Girish, who is one of the main guys to raise funds here in Orlando for them. They're still debating, and I said, no, we have a running system for the last 6-7 years. I'm in India doing this. So don't reinvent the wheel, because you have no time to go and handle their problems. Every school has its own problems, right? So you should be able to get in and get out, or lab assistant gets in, gets out.
Right.
Otherwise, you're
Yeah.
stuck.
Yeah.
So that's what I've been telling them. So maybe we can set you up, and I want to go to ACL too. But if they don't have the very basic,
That's hard.
very hard, right? So we have an organized system, that way you can slowly, and now you guys can mentor the engineering students.
So what we were thinking is
That's
like
because they have a lot of things they need right now, what you guys are doing. Right? They're putting NVIDIA chip and doing all these things.
Yeah.
So you guys are, this is what I've been telling them. Just do triple redundancy. Very first redundancy should be just your attitudinal calculation using what you're doing right now. Just with 3 sensors, height sensors, you should be able to get it. Imagine you have no cameras, you have no IMUs. Just with those, how do you calculate attitude, like what you guys are doing? So that's great. Now these college kids will learn from you. You see what I mean? So, and then I'm trying to get those college students to help those rural schools.
Yeah, that'll be good.
That way it's easier for management. And I mean, we can work out,
Right.
so depending on things, right? So
Are you talking about one school or a lot of schools?
I am talking at a cluster of 6 schools at a time.
Okay.
That's how we do. One day a week, this assistant goes to one school. So
Okay.
6 schools.
6 schools.
One is made the hub school, 5 spoke schools.
Okay.
Because they may not have all the facilities.
That's right.
So they come to a competition like this to a hub school. At least 3 times a year we can have a competition.
Okay.
They come and learn.
Okay.
And in the mean, the classes are in the Gurukula.
Okay.
If they don't have the internet, we'll put it on the server. They go listen to it. And choosing a team also is complex thing, because everybody wants their kid.
Right.
Right? They're stopping us and, sir, I want to pay money for this keyboard. I want my child to.
Yeah.
So you see,
It's hard. Yeah.
very hard. But to keep it manageable, we try our best. And we tell them, if you only do your content typing first for your classes, then we'll let you come in. Right? So then they're able to. And school closes exactly and the bell rings, they're gone, they're going to lock up. They don't have time like you guys. They have absolutely no time. The bus comes, this next bus is 3 hours later. They can't miss the bus, the girls cannot be there. A lot of challenges.
Yeah.
The best way is to at least quest their thirst for knowledge using the experiences you guys have through your lessons.
Yeah.
The next step is maybe a kit or so you guys do, we can make them learn it from school to school. Whatever you guys say.
Yeah.
Small things, maybe just an arm going up and down, the controller and sensor or something, whatever you guys have spares lying. Then they can start learning and playing.
Right.
You can do that.
Yeah.
Yeah, go ahead. Anybody next who wanted to explain? So the thing I had the question was, one is a controller, right? So you have 2 different controllers, you said, right?
Yeah.
2 hubs, 2 different hubs.
Hubs. Is that by the one just for the motion and the other one for your elevation and other things, or?
Yeah, so like we run different things. If we there's not enough ports on this to run all of our systems.
Okay.
So we have another hub that holds the other systems. They communicate using a data cable.
Okay.
They can have up to 8 motors.
Yeah, so we can have up to 4 motors on this one, 4 motors on this one.
It's an extension of the
Yeah.
control hub.
So it's
an
called
extension hub.
expansion hub.
Expansion.
So it just allows you to plug in more ports,
Oh,
more
I see.
devices.
I see.
Yeah, they handle, there's no
The
separation of what they
control
handle.
hub is what
Yeah.
the
There's-
programs downloaded on.
Oh.
There's no software on this at all.
Oh,
It
there's-
all goes back to this controller.
Controller?
Yeah,
Okay.
and we have all the ports here too.
Oh, I see. I
Yeah,
see.
so-
Now that controller, the one you're using, it's called what you said again?
Rev
Rev
control.
Rev
Oh,
control.
rev control. Okay. Now they're all DC motors, right? No steppers in this.
Yeah.
DC.
Okay. And for encoding, and then you're using the dip switches, right? For tripping.
Yeah.
Okay.
So
They
we have
have
one in
a-
our intake.
Oh, is it?
So when we detect it, we can see that when we picked up one.
Oh, I see. What sensor is that?
It's just
a
a limit switch in there.
light sensor?
Limit
Yeah,
switch,
limit switch,
like-
yeah.
Oh, okay.
Like on 3D printers. like,
Oh,
have it.
okay.
Yeah, and then we have 2 on the back.
And this tubes that you have, is it for suction? It's like a pump?
Those are just to like manage the wires.
These here.
No,
yeah.
no, I'm talking the tubes in the front.
Oh, these.
Oh,
There,
surgical
eh?
tubing.
Huh?
Yeah.
It's just like flick it in easier.
helps intake the
They like
pixels
hook onto
faster.
Oh, I
the.
see, I
yeah.
They
see.
hook onto them to pull it in.
Pull it in.
And then these are the switches he was talking about. They're commonly found in 3D
Yeah, yeah,
printers.
yeah, correct, yeah, yeah.
Yeah,
This is a
there's
dip
one-
switch. We call it dip switch.
Oh, okay.
Yeah.
Yeah.
Good, good. So good. So you guys, so the programming is, and that is Android based.
Yeah.
Yeah.
And
So it runs on an Android app
Okay.
inside the hub, and
Oh.
we just program different, I guess.
Nice. Okay. Yeah, we